Chapter 7, exponential functions. So an exponential function looks like this. Y equals c to the exponent of x. So for it to be an exponential function, your exponent has to have an x in it. Your exponent won't just be 3. It would be 3x, for example. Okay? Also, c has to be a positive number. So c is like your base, right? What's being raised to the exponent. Okay? So it has to be positive. So no negatives, but also it can't be equal to 1. Okay, so we're going to do some examples of how to recognize exponential functions, but those are the main rules. Okay, few things here. If c is greater than 1, okay, the function will increase. Okay, so the function increases if your base, that c value, is greater than 1. So a 2, for example, okay? And what that means is the graph will raise as we travel to the right. So your graph is going to look like that. So all of our graphs are kind of half curves today. Okay, the other scenario, if c is within 0 and 1. So remember I said it can't be negative, right? So I'm never going into the negatives, and I also said it can't be 1. So you'll notice I have no equal signs with my 1s, right? Because 1 is off limits. We are either strictly greater than 1 or strictly less than 1, but not negative. So if it is between 0 and 1, in other words, if it's a fraction, essentially, okay? Usually it would be a fraction, like 2 over 3, something like that. The function decreases. And what that means is it lowers as we travel to the right. So it would look something like that. Okay? Next thing, there is typically a horizontal asymptote. So we've only had vertical asymptotes up to this point. Think of tan graphs, right? There is a horizontal asymptote where y equals 0. Okay, so we will see in all of our graphs a dotted line on the x-axis. Okay, the only time it would not be directly on the x-axis is if there's a vertical translation. So if we're moving the graph up or down, then the asymptote would move. Okay. And third one here, sometimes you might see negative exponents. That's allowed. Okay. So if you ever have a negative exponent, you guys learned this in Foundations 10, way back yonder, that if you have a negative exponent, you take the reciprocal of the base, right? So this base is actually c over 1 raised to the negative x. You just flip that. You have 1 over c. And when you take the reciprocal, then that exponent becomes positive. Okay, we learned that in Foundations 10. So just flip the fraction or flip the base, the exponent becomes positive. Okay, so I'm just going to show you here an example of an increasing function. And I made a typo on your sheet before I caught it, before I photocopied. I just copy and pasted increasing, and then I forgot to actually erase increasing in the second title. That should say decreasing. I'm not giving you 2 examples of increasing that look totally different. Change that word to decreasing like I have. Okay, so here's an example of an increasing function. It is increasing. We know it will be because the base is 2, right? And that's greater than 1. That's what the rule above said. So my base is greater than 1, so we know it's increasing, which means it's going to raise to the right. Now, what we're going to do to kind of pick this apart a little bit is find some points on here and just see what happens. So remember way back in grade 9, you guys would create tables of values and your teacher would say, just use x values, -2, -1, 0, 1, and 2. Remember that? Okay, those are kind of like the basic table of values, x values we use, and we're not really given any. All right. And also it's smart to choose those because if you look at the graph, you have all of those x values on your graph. So it makes sense. We're going to practice finding what the y value would be. So your second heading is always your equation in terms of y. So y equals 2 to the power of x. And we're just going to see how that works out. So if you want to find your y value when x is -2, like obviously we know it's going to be it's that value down there. So our y value is really tiny. What you would do is you would take your 2 but just raise it to whatever you chose your x to be. X is negative here. So remember what this means is you flip that base, keeps doing that. You flip that base, so it's actually 1 over 2 now, and that exponent becomes positive. So you're going to be doing that a lot in this unit, having to flip your base and change the exponent to positive. Okay? And then you square both values. So that means your y value is 1/4 or about 0.25. And if you look at that circle dot, yeah, that's way down low. That's at about 0.25. That makes sense. Okay, you repeat the process. I'm going to go quicker now. So now it's a -1. That's 1 over 2 to +1. Well, that's just 1 over 2. So when x is -1, which is right here, it should line up with 0.5, and it does. Okay? So that's what happens when your exponent is negative. Let's look what happens when your exponent is 0. Anything to the 0 equals 1. Anything to the exponent of 0 equals 1. It's on the wall. You learned it in grade 9. It's true. Okay? So when x is 0, y is 1. That's that point right there for sure. What? It's on the wall back there. 39 to the 0, top right corner poster. 39 to the 0 equals 1. Every non-zero number to the exponent of 0 equals 1. Okay? Now, when your exponents are positive, life is easy breezy. 2 to the power of 1 equals 2. 2 to the power of 2 equals 4. If you look at those points, that makes sense. Okay? So an exponential function, if we look at a pattern here, we just times every answer by 2. 1/4 times 2. 1/2 times 2. 1 times 2. 2 times 2 is 4. Okay, so there's a pattern. We times by 2 every single time. Okay, so if we times our y values by 2 every single time, they increase. That makes sense. Okay, and also you can see here there is an asymptote at 0. You'll see that that curve approaches the x-axis, but once it approaches the x-axis, it kind of levels out, okay, and doesn't actually cross. All right. Let's show an example of decreasing. I won't do as much detail here. It's just kind of the opposite. So again, if we were to create a random table of values with some x values, okay, I'm even going to cut a few more corners here because I want to move on to the next thing. Instead of choosing 5 values, let's just choose 3 values just to shorten this up a little bit, but I still will choose 1 negative, 1 0, and 1 positive. This time, your equation is y equals 1/2 to the power of x. That's the equation I gave you. Because our base is a fraction, or our base is between 0 and 1, we know it's going to decrease. So let's see why. So if you take your equation, I have 1/2 to the power of -1. I'm plugging in my x value. My exponent is negative, which means I would flip my base. It becomes positive, but all that just becomes 2. Okay? So when x is -1, y should be 2. That's that guy right there. Perfect. All right. Next one, 1/2 to the power of 0. Anything to the power of 0 is 1. So when x is 0, y is 1. And finally, 1/2 to the power of 1. Well, who cares? It's just 1/2. So when we get to x is 1, we're down to about y being 1/2. Okay, so that's an example of where your values decrease. And if you look at the pattern with your y's just get cut in half every time. In the previous one, they were multiplied by 2 every time. So of course we got bigger. Here, when we're decreasing, we're cutting them in half every time. So we get smaller or lower. Okay. I just want us to state if the following are exponential functions or not. So this guy here, you have y equals, you have a random base, 3 over 10 to the power of x. Okay, you have to check, is your base positive? Yes, it is. And does your exponent contain an x? Yes, it does. Okay, so yes, positive base, exponent with x. So both of those things get checked off. Okay, B, no, your base is negative here. Negative base. That's not allowed. That's not an exponential function. This one, any takers? No exponent without an x. Your exponent needs to have an x. Your exponent there is just 4. No deal. Okay? This one, all right. You can look at the base and think, oh, Miss Wolf didn't really talk about the base being a binomial. It doesn't matter because as soon as you look at that, your exponent doesn't have an x in it. So it doesn't matter if it's a binomial base because the x isn't in the exponent. That is not an exponential function. So again, we have an exponent without an x in it. That's a problem. Okay, this guy here, yes, your 8 is positive. Your exponent contains an x. Beautiful. Done. What about this one? Yes or no? Why? Our base is not negative. Our base is positive here. In order for a base to be negative, it would need to look like that. We learned this in grade 9. Little trip down memory lane. This and this are two very different things. This means negative 8 times 8. This means negative 8 times negative 8. One equals negative 64, one equals positive 64. They are very different. Okay, so when it's in the brackets like that, the base is negative 8. The negative is included. When it's outside of the brackets, it is not included. It's not repeated. It's just kind of floating around. So here, erase this. This is an exponential function because the base is 8, not negative 8. Okay? That's all good. So be careful with that. All right, moving on. Another kind of easy one, we're just going to get familiar with whether these should be increasing or decreasing functions. So they move up or they move down. All you got to do to figure that out is look at your base. Is it greater than 1? Because if so, it's increasing. Is it less than 1, but not negative, right? Then it's decreasing. Okay, here, this would be an increasing function. I'm not even going to write increases. You guys can if you want. I'm just going to show you. It would increase, and the reason being is c is greater than 1. This guy would decrease because your c is in between 0 and 1. It's a decimal or 1/4. It's a fraction, right? Here, what about this one? Increases or decreases? It decreases because this value, if you need to convert it, is 0.9. That is between 0 and 1. So it decreases. Moving up, 1.3, it's a decimal, but it's still greater than 1. Okay, so if c is greater than 1, we are going to increase. Okay, this one, 12/11, it's a fraction, but see what that fraction is worth. 12 divided by 11 is 1 point something, so it is greater than 1. So c is greater than 1 here. We are going to increase 2 more. And if you look at the last two, just take a look at f and g. I want you to be able to distinguish the difference between f and g. It's both 3/1000. But if you look at f, what is your base in f? The 3, because the 3 has the exponent, right? So to figure out if it's increasing or decreasing, just look at the 3. Because c is greater than 1 or your 3 is greater than 1, we are going to increase. The 1,000 is just kind of an afterthought. But with this guy, because it's all in brackets raised to the power of x, that whole thing is the base. So 3 divided by 1,000 is very, very, very tiny, 0.003, right? And so that decreases because that is in between 0 and 1. Okay. We are going to quickly sketch 2 graphs from scratch. We're going to sketch, we're going to state the domain, the range, the y-intercept, the x-intercept, if possible. I shouldn't have even written that. We won't have x-intercept today because we have that asymptote on the x-axis, so it shouldn't cross. But when we do transformations and we shift them, then we might have one. But today we won't. All right. Okay. Also tell me if it increases or decreases. Okay. So we are going to draw in our asymptote vertical line where y is 0. Okay. I am going to create my table of values. Because we're actually drawing the graph from scratch, let's do a few. We'll do -2 to 2 again. My equation is y equals 3x. So you just got to plug in, and you would have 3 to the -2, which is actually 1 over 3 to the 2, which is 1 over 9. Then you would have 3 to the -1, which is just 1 over 3. You would have 3 to the 0, which is 1. And now you can see a pattern happening. Clearly, I am just multiplying each fraction by 3. So if I now multiply 1 by 3, that should be a 3. That should be a 9. Okay, so you can see the pattern if you so choose and just kind of quicken up your work. All right, so let's draw these points as best as we can. We're going to have to estimate, of course. So when x is -2, right here, you know what? Let me spread out a little bit, actually. I have all this graph to use. I'm going to go every 4th, just to not make it so tight on here. Okay, there's my x values. I do have to go up to 9, though, for y, so I will keep y as that. So my y's are going to be really squished, but that's okay. All right, so at -2, my y value is 1 over 9, so you can convert that to a decimal, okay? Or if you want, you can start with the positives, 2 and 9. It doesn't matter which end you start on. Okay, we are obviously an increasing function because my base is positive. So I know 1, 2, 3, 4, 5, 6, 7, 8, 9. That's actually my top point because I know my graph is going to kind of trend like this. So that's my ending point, and they're going to come down smaller. Okay. Then I have when x is 1, y is 3. When x is 0, y is 1. So I'm there. And now I get into the squishies. You're going to barely see them. When x is -1, y is 0.3. That's what 1/3 is. So 0.3 is like right there. I can barely draw that point. You know what I mean? Like you'd barely see it. We just know that it's approaching the asymptote and it's really close. So you could even honestly forget about that point. Just you can see how your graph is trending now, and it would just trend this way, and it would just kind of level out at the x-asymptote, or the asymptote where the x-axis is. Okay? All right. The question also asks us to state domain and range. So domain, x is an element of all real numbers. We got the arrows on each end. But my range, my y values are strictly above the x-axis. So my y values are greater than 0, not equal to, because we don't cross. Yes? And just remember, in your textbook, you'll probably see this portion too. That just means that y does go up forever, and we know it just only hits real numbers up there, okay? And I also asked you if this increases or decreases. Clearly, we can see this increases. It also asked me for my y-intercept. Well, your y-intercept was actually found in your table of values. Your y-intercept is when x is 0, right? So this guy right there, that is the 0.01. That's your y-intercept. And we're done. We're going to do one now where we are decreasing. Then we're going to do a little bit of a tiny word problem about rabbits. And then we're going to be done. Okay? All right. This one. Before we even graph it, we know we're going to be decreasing because our base is a fraction between 0 and 1. Okay? Let's create my table of values. My x values. Typically use those. This time my equation is 1/3 to the power of x. So I have 1/3 1/3 to the power of -2. This is the first time we've seen it like this, where it's negative, but it's already a fraction. Same rules apply. Flip that base, so it's now 3/1. The exponent becomes positive, so it's 9. So we start high because we're decreasing, okay? Then I have 1/3 to the -1. Flip that, that's 3 to the +1, that's 3. And right away, you should be able to see your pattern. I'm dividing by 3, okay? This one, to prove it to you, 1/3 to the power of 0 is 1. Boom, I just divided 3 by 3. I got 1. Divide 1 by 3, so it's 1/3. Divide that by 3, it's 1/9. Okay, patterns will always exist with exponential functions. Okay, draw in your asymptote. Okay, y equals 0 asymptote. Again, I'm going to spread my x values out here just to not be so cramped. But I cannot do that for my y values. I got to go up to 9 again. Okay, so here, -2 and 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right there. -1 and 3. So we can see we're trending down. Makes sense. We're decreasing. 0 and 1. There's my y-intercept. Okay. And then when x is 1, again, we have the situation where I'm right there, 1/3, and I can't even draw 1/9. So you can just trend or see the trend here. You approach the x-axis asymptote. Okay. Let's just do domain and range quickly. Again, element of real numbers. Range. Y is greater than 0. So you can see, again, our domain and range are also always the same, unless we have translations, of course. Okay, my y-intercept is this guy right here, or you can locate it here for me, 0, 1. What else did I ask for? Oh yeah, if it increases or decreases, this obviously decreases. There is no x-intercept, so we're just going to leave that. Okay, all right. So next question. Sorry, I see people still scrambling. Maybe I'm going too fast. I'll leave that up for a second. Next question, last question. We have rabbits. All right. So the number of rabbits represented by R after n months is represented by R equals 200, then times 2 to the power of n. Determine the population for 0 months. Okay, so if we have bunnies who are mating, okay, and then they're having more bunnies will mate, and more bunnies will be born, and more bunnies will mate, and more bunnies will be born. Yes? That's what exponential growth is. The more bunnies there are, the more bunnies there are. Yes? Okay? So this is an exponential function. It's going to show us how much growth happens from 0 months to 4 months to 1 year. So at 0 months, that means my n equals 0. Okay? Because it tells me n is months. So n is 0. So my number of rabbits is 200 times 2 to the power of 0. I'm plugging in n with 0. So that's 200. Anything to the power of 0 is 1. So after 0 months, so essentially when we're starting this experiment, or when we're just starting to count at month 0, we're starting with 200 rabbits. Okay? We've got 200 rabbits. Then we go let them do their thing and make babies. So after 4 months, how many more rabbits would there be? So now we are going to plug in a 4 with our n. Do the math. 200 times 2 to the power of 4 is 16. So after 4 short months, we would already be up to 3,200 rabbits. Okay. Now, let's see after 1 year, how many there would be. Any guesses? What are you thinking? Like millions, thousands? What are we thinking? A lot. Okay, we'll go with that. So it's 1 year. What do I put in for my n? 12. Very good. Can't even stump you guys. 2 to the power of 12 is 4,096. So that means after 1 year, we would go from 200 rabbits to 819,200 rabbits. That's exponential growth, baby. The more babies there are, the more mating there is, the more babies there are, right? So you might see a couple word problems like that. Just plug into the formula and solve. Okay, not so bad. Let me end this video. Your assignments should be listed at the bottom there of your page, right there. 342, 1 to 7. This will be due Monday.